What's up, y'all? So, 6.3 is all the applications of the Euler-Lagrange equation. So basically, it explains why it's useful, why it's cool. It, I will tell you, chapter 7, it's cooler. It's better in chapter 7. But this is like the basics of how it works. And what we're going to do that is basically the book throws you back to section 6.1 and it's like, and now we're gonna solve them. So we're gonna go back and we're gonna solve them. So the first one that we're gonna do is the shortest path between 2 points. And then I took the equation that we got from section 6.1 and I just sort of rewrote it here. That way we can start where we left off. And basically all we're doing is we're identifying what we call f, and that's the equation of y prime, and x. If you want to know why, that would be chapter 6.2. But basically, we're going to call that just what is inside the integral. And I'm going to write it with an exponent instead of a radical, just for simplicity's sake. And then what we're doing is we're taking the Lagrange equation. So I'm going to write it down here for that way so that we know it. That's why I'm going to write it down, because we like to know things. Yeah, so that's Euler-Lagrange's equation, and we're just going to use it right now. So we're going to start by saying the derivative. What did I just do? So the derivative of f with respect to y. And there is no y, so we just get 0. So with the Euler-Lagrange, you're literally just looking for that variable and that variable alone. You know, like, how does this variable relate to the other variables? If it's a function, no, just look for the actual variable itself. And then we're going to do it in 2 steps. So we're going to do a dx right there, and scroll down a little bit. We're going to take the derivative of f with respect to y prime, and when we do that, we get y prime over 1 plus y prime squared to the 1/2. No, don't mind. Okay, so that's just chain rule. And then we're going to do it, so we're going to do it again. So we're going to take the derivative with respect to x of what we just took the derivative of. So we're going to get 0, because there is no x. So all that really tells us is that this function right here is equal to some constant. So we're going to rewrite it. That's cute. We're going to rewrite it down here as just c equals the function that we had. So I forgot what it was. Y prime over 1 plus y prime squared to the 1/2. And then I'm gonna solve for y prime squared. That way I can get rid of the radical entirely. I just don't want to look at it anymore. This is gross. In physics terms, it's just gross. So we're gonna get that and y prime squared. So at this point, I'm just literally gonna quote the textbook from you, because this is what the textbook advised me from here. It was like, or with a little bit of rearranging, y prime squared is a constant, and this implies that y prime of x is a constant, which you can call your m in the point slope formula. So it just, you found the slope. So all of this equals m in y equals mx plus b, which is good because it goes into this a bit more in like section 6.4, but it actually states in the textbook that the goal of Euler-Lagrange's equation is to know how your coordinates like move with time. So by knowing its slope, we know what happened to it over time. So we got exactly what we wanted to do. Uh, just sort of in a funky way, I guess. So the next part that we're going to do is something called, I'm going to spell it out because I'm going to be really honest with you, I don't know how it's pronounced, and I don't feel like trying. So I'm going to call it Brock. So we're going to solve Brock. And you'll see why I call it Brock. I'm going to make it a little bit easier to see. Yeah, so we're about to just solve Brock a little bit. What Brock is it's simply just here. Let me read the textbook's words of it. It's we built a track of a frictionless roller coaster so we can release from point 1 to point 2. So you're just going down a slope. And it's got a graph that I'll draw for y'all. Let me see. There it is. Okay. It's a pretty simple graph, and it looks like this. This is X, this is Y, and there it is. So that's exactly what it looks like, and it goes from point 1 to 2. I'm not going to draw points because they don't end well for me. And what it's having us do is in section 1.1, we did the whole like total time thing. We're going to do that again. So we're honestly going to snake that equation to say that the time it takes to, time has an E, from point 1 to point 2 is going to be equal to the integral from point 1 to point 2 of ds over v. Except this time v isn't, it doesn't have anything to do with light. So that's basically what we got there. And we're gonna look here where we have ds. So that's that at some points it acts like a straight line, whole jive and deal. So I'm gonna write it back out here. This is mirroring section 6.1 so far. But what we're going to do a little bit differently here is to get rid of the two variables, we're actually going to make x a function of y, just because it's a one-to-one function that way. And that's much better to deal with. So ds is going to be equal to, it's literally just the same as in section 6.1, just flip your x's and y's. So it's going to be x prime of y squared plus 1 dy. Yeah, great. So that's going to be our s, and then we're going to plug it into here. But one thing to note before that is that we are actually, the textbook gives us a v, and it's very familiar, so I'm going to write it here in blue. V equals the square root of 2gy. So that's very familiar from just like physics 251 and any high school physics, but that's just the given velocity in the textbook. So what we're going to do from there is we're going to rewrite into that integral so that time it takes to go from point 1 to point 2 is going to be equal to the integral from, it starts at the origin, so its initial points can be 0 to a y2 value. And we're going to take the integral of the square root of x prime y squared plus 1 over that square root of 2gy dy. And then we're going to realize that this is our F in Euler-Lagrange, or Lagrange, whatever, which I'm going to write again out here. So we keep it in mind. Plus, I wanted to show you that one thing changes in here, where in this problem, we've redefined exactly what's a function of what. So our Lagrange, or Lagrange is going to read like this. There's something to be cautious about of when you define what while using Euler-Lagrange. So it'll work for just about any coordinate system. You just want to make sure you're using it right. So now that we've got that, we're gonna take, we're gonna take the derivative of our f function with respect to x, which is gonna be 0 because there is no x's in it. And then we're gonna bring down our dy, and we're gonna take the derivative of that function with respect, with respect to x prime. And we are going to get, fasten your seatbelts, it's going to be a bumpy ride. What we're going to do is, actually real quick though, before I even bother doing that, I would like to point out that this right here, this square root of 2g, I can actually bring out in front of it so I don't have to think about it. Which I personally enjoy not having to think about it. Be honest with you, I don't want to think about it. That way, when we take our derivative of f with respect to x, it's a lot easier. So we don't even have to include the square root of 2g in our f function because we don't care about it. It's a constant. Constants are constants. That's how constants work. So write that all out for y'all. So what we end up getting is x prime over the square root of y times 1 plus x prime. And then I think that's disgusting. So first of all, let me point out that this has to be true, so that if we take the derivative of y of this function with respect to y, it'll give us 0. That means that this function has to give us a constant. If we knew what y was and we knew what x prime was, it would give us a constant. We just can't see it without knowing. So we're going to take that information that we know and we're just going to use that. But I also think the equation is ugly, like I said before. So I'm going to take, oh my goodness, stop that. I'm going to take all this and I'm going to square it. That way I don't have to look at that ugly radical. So constant squared is just a constant, so I'm going to keep that there. And then x prime over y times 1 plus x prime. So that's going to be our new thing that we're working with. This is supposed to be squared. And in here, this is supposed to be squared. I forgot a few things. Oh, don't do that. Please don't do that. Okay. We're just going to all pretend like we know that I meant to put something there. Well, now it works. Guys, I'm going to be honest with you. It's not going too well. Okay, there we go. So now that we've got that, we're just gonna, so we're gonna solve it a bit, but I'm gonna be real honest with you here. The author pulled something out of thin freaking air, and he was like, oh, look at this. We're gonna use this. And I was like, why? And he was like, future convenience. And I was like, why on earth would you know why to use that? And he was like, it's for future convenience. And I was like, but you know what? I guess it was for future convenience. So I'm gonna pull something out of thin air for future convenience. And we're gonna say that C equals 1 over 2A. Don't ask, because he won't tell you. For future convenience. So now we're going to rewrite that so that 1 over 2A equals x prime squared over y times 1 plus x prime squared. And now we want to solve for x, or x prime in this case. And in order to do that, we're going to, first of all, make our lives easier, stop using fractions. Nobody wants that. Hey, back there. 2A x prime squared. All right. So basically from there, pull that down. I'm just gonna solve it for x prime, doing whatever the heck I did. I want all the x primes on one side. That's what I did. So I just sort of like move them. The textbook kind of skipped all this stuff, and I went, what? And it said, sucks to suck. And so I just did it. Because that was rude. That was a very rude thing to say to me, textbook. Okay. Now that I got that, I'm just going to quickly solve for x prime here. Just going to write it down. We're distributing, just so y'all are aware. So I guess that's convenient. I wouldn't have been able to pull that randomly and be like, when this problem ends, this use of C will be convenient. So at some point, it's just nice to trust. And then we're just going to find x of that. So basically, x is just the integral. And that would be your little fastest path. That's all under a radical. And dy. So that's sort of what all that's about. And then the textbook goes into more substitution and sort of solves the integral for you. So I'm just going to write down what they have written down. I don't feel like writing down the whole substitution process and all that. So what they end up getting is that x, so real quick, I'll tell you that their substitution was that y equals a of 1 minus cosine theta. And so that they get a times theta minus sine theta plus a constant. And then when you solve for y, you end up getting a times 1 minus cosine theta. And then your original y was that 0. And actually the original x is that 0 too, so don't care about that constant. You'll find that most constants we don't care about. So the things to note from this is that the Euler-Lagrange generates a path that makes the original integral stationary. So whatever path isn't moving is the shortest path. And the fact that that occurs is what makes the Euler-Lagrange equation works, and what makes the the integral stationary is that the Euler-Lagrange equations work. So basically, if you have one, you have the other, and if you have the other, you have the one. A little bit of circular reasoning, but that's honestly all this chapter was about. So those are the applications. It gets cooler in chapter 7, but that's basically how it works in chapter 6.